In Philadelphia in 1828, an extraordinary wagon appeared on streets where almost every moving vehicle still depended on animal power. Its proportions alone made it difficult to mistake for an ordinary carriage. Two enormous driving wheels dominated the rear, each reported to be roughly 8 feet in diameter. Smaller wheels at the front provided steering. An upright boiler occupied part of the rear structure, while a horizontal steam cylinder and mechanical linkage supplied force to the axle. There were no horses ahead of it. Whatever moved this machine had to be generated on board, controlled by its operators, transferred through iron components, and delivered to the road beneath its wheels. A later 19th century engineering account identifies the builders as Nicholas and James Johnson brothers, who operated a small engineering establishment on Penn Street in Philadelphia's Kensington district. Far less survives about the men than about the machine associated with them. Their private ambitions, conversations, education, finances, and personal reasons for undertaking such an experiment remain obscure. That absence matters, because it changes how the story must be told. There's no reliable basis for portraying them as prophetic inventors dreaming of a motorized America. The more defensible evidence lies in the wagon itself and in later descriptions of the trials it underwent. Philadelphia was not unfamiliar with steam technology. More than 2 decades earlier, Oliver Evans had already experimented with high-pressure steam and an unusual machine capable of moving on land as well as operating in water. Thomas Blanchard would also become associated with early American steam road experimentation. Such work makes any claim that the Johnson brothers created America's first self-propelled vehicle difficult to sustain. Their experiment is more interesting when stripped of that kind of priority myth. What Nicholas and James Johnson attempted was a recognizably road-going steam wagon, a machine meant to propel itself through ordinary streets rather than remain attached to a factory, mine, or vessel. The distinction created an engineering problem that stationary steam engines did not face. A fixed engine could sit on a foundation while fuel, water, maintenance, and working machinery were arranged around it. A road vehicle had to carry the apparatus required to produce its own motion. The boiler added mass. The water inside it added more. Fuel had to be carried or obtained. The cylinder, linkage, axle, wheels, frame, controls, and operators all became part of the load. Every improvement in mechanical independence therefore imposed another burden on the engine. The machine had to move not only passengers or cargo, but also the equipment that made movement possible. Road conditions complicated that equation. Philadelphia's streets were not designed around motor traffic. They carried carts, coaches, wagons, pedestrians, and horses, and their surfaces could be rough, uneven, or unpaved. A horse could change its footing, alter its pace, and respond instinctively to obstacles. The Johnson wagon had only its steering geometry, wheel contact, mechanical controls, and the judgment of its operator. If a rut pushed the front wheels aside, if the road rose unexpectedly, or if a turn required the machine to change direction quickly, the response had to come through hardware. That made propulsion only one part of the problem. The vehicle also had to remain steerable and manageable while carrying a boiler and working machinery that an ordinary carriage had never been expected to support. The Johnson brothers were attempting this before an automotive industry existed. They could not select a standardized road engine, proven steering system, transmission, chassis, braking package, or commercially manufactured set of components. Whatever they built had to emerge from the engineering practices available to them. The surviving description suggests a design that combined traditional wagon construction with steam machinery rather than replacing one technology with an entirely new form. The smaller front wheels remained recognizably connected to carriage steering. The great rear wheels became the powered pair. Between them, the engine arrangement transformed reciprocating motion into axle rotation. This hybrid character is one of the most revealing aspects of the machine. It shows engineers trying to solve a new problem with familiar mechanical languages, rather than beginning from a blank sheet of paper. The reported dimensions of the rear wheels make the wagon visually striking, but the significance of their size should not be exaggerated into an undocumented design philosophy. Large wheels interact differently with rough surfaces, change the distance traveled per axle revolution, and influence the mechanical relationship between torque at the axle and force at the road. Those are physical consequences of the arrangement. They do not tell us exactly why the Johnson brothers settled on that diameter. The same caution applies to the rest of the vehicle. The historical record describes an upright boiler, a single horizontal cylinder, a connecting rod, and a crank placed near the center of the driving axle. It does not provide a complete modern specification sheet. Horsepower, exact boiler pressure, vehicle weight, fuel consumption, maximum speed, range, and detailed braking performance cannot be supplied honestly without evidence. The fragmentary nature of the documentation is therefore not an invitation to complete the machine imaginatively. It is part of the historical reality. Enough survives to understand the mechanical concept in the trials that followed. The wagon was not simply an oversized carriage with a mysterious engine attached. Its layout formed a connected system in which the boiler produced the working steam, the cylinder converted pressure into linear movement, The connecting mechanism redirected that movement, and the rear axle delivered rotation to the wheels. Before judging whether such an arrangement could survive Philadelphia's streets, however, it is necessary to understand exactly how that chain of energy worked. The Johnson machine becomes less mysterious once the force is followed from its source through the piston into the crank and finally outward to the road. The sequence began with heat. Fuel burned beneath the boiler, transferring energy into the water contained within it. As the water was heated, steam formed and pressure increased. The boiler's purpose was not to propel the wagon directly, but to create a controlled supply of pressurized steam that the engine could use. When admitted into the horizontal cylinder described in later accounts, that pressure acted on the piston and forced it along its stroke. The piston moved in a straight line, but the rear wheels required continuous rotation. A connecting rod therefore carried the piston's reciprocating motion toward a crank positioned at or near the center of the driving axle. As the rod pushed and pulled, the crank turned. Rotation passed into the axle, and the great rear wheels rotated with it. At the road surface, the wheels pushed backward against the ground, allowing the vehicle to move forward. That was the complete mechanical argument of the Johnson wagon. Heat became pressure, pressure became piston movement became axle rotation, and axle rotation became tractive force. Each stage introduced losses and limitations. Friction in bearings and joints consumed energy. Leakage could waste steam. Poor alignment could increase resistance. Road irregularities could disturb the frame while the linkage was operating. The engine, therefore, had to generate enough useful force not merely to turn its own mechanism, but to overcome the losses created throughout the entire vehicle. The boiler determined whether this could continue for more than a brief demonstration. A cylinder might make several strokes on stored pressure, but sustained motion required steam to be produced at roughly the rate the engine consumed it. When the wagon encountered a grade, the demand increased. The engine now had to raise the mass of the complete machine against gravity. More steam had to perform more work, and the boiler had to respond without allowing pressure to fall excessively. A later engineering description of the Johnson trials is especially revealing on this point. It indicates that the machine showed a deficiency in both boiler power and cylinder power on the rough roads over which it was tested, even though it could continue operating for significant periods and negotiate substantial elevations. That is far more informative than simply calling the wagon powerful or underpowered. It shows that the basic system worked while operating close enough to its limits for inadequate steam generating and engine capacity to become apparent. The Johnsons had achieved propulsion, but they had not eliminated the compromise between machine size, steam production, and useful tractive effort. The single-cylinder arrangement intensified some of those demands. With one piston supplying the working strokes, turning force at the crank would naturally vary through the rotational cycle. At favorable crank positions, piston force could create strong leverage. At less favorable positions, the same linear force produced less rotational effect. Momentum in the rotating parts could help carry the mechanism through those weaker positions once the wagon was moving, but starting from rest could be more troublesome depending on crank position. This is an engineering consequence of the layout rather than a documented complaint from the Johnson brothers. The surviving record does not tell us how they discussed the issue or what specific procedures they used to address it. What the arrangement demonstrates is the simplicity and severity of early steam road engineering. Fewer major working parts could reduce mechanical complexity, but simplicity did not automatically produce smoothness. The 8-foot rear wheels magnified the unusual appearance of the system. Their large diameter meant that each complete axle revolution carried the wagon a considerable distance. It also meant the engine had to accelerate large rotating structures while overcoming the weight and resistance of the vehicle. Once those wheels acquired momentum, that momentum could help maintain movement. Yet it could become a liability when the wagon needed to change speed or direction quickly. The front wheels handled steering rather than propulsion, so direction and motive force were mechanically separated. That division seems ordinary in later vehicle design, but in a steam wagon adapted from carriage practice, it created a difficult coordination problem. The rear of the machine was continually being driven by a mechanical power source, while the front had to guide the resulting mass through streets built for slower, animal-controlled traffic. The operator could not rely on the instinctive response of a horse to a curb, pedestrian, wagon, or sharp turn. A control input had to change the position of the steering wheels, and the mass of the rest of the vehicle then had to follow. The upright boiler added another concentration of weight, heat, and responsibility. Later descriptions mention a weighted safety valve arrangement, evidence that pressure control was part of the practical system. A safety valve did not improve propulsion. It existed to prevent steam pressure from rising beyond acceptable limits by allowing excess pressure to escape. That distinction illustrates the dual task faced by anyone operating the wagon. The engine needed enough pressure to perform useful work, while the boiler had to remain within conditions that could be managed safely. More pressure was not automatically better. The useful operating range depended on the strength of the vessel, the condition of its components, the water level, and the demands being placed on the engine. Water created its own compromise. The boiler needed a sufficient supply, but water was heavy. Carrying more increased the available operating reserve while forcing the engine to haul additional mass. Fuel posed the same contradiction. A larger supply could extend operation, but added weight before it produced any useful energy. A stationary engine could be surrounded by these resources. A mobile one had to make choices about what to carry. Even lubrication and mechanical adjustment became harder once the entire assembly was moving over an uneven surface. The crank, rod, axle, bearings, wheels, and supporting structure had to remain aligned closely enough for the transmission of power to continue efficiently despite road shock. A mechanism that ran smoothly when supported inside a shop could behave differently when every wheel impact sent forces through the chassis. The wagon had to work while being continuously disturbed by its own movement. That was the hidden difficulty behind the spectacle of a self-propelled carriage. The Johnson brothers had assembled a chain of mechanisms capable of generating tractive force, but the street would decide how useful that force really was. Once the boiler was producing steam and the crank began rotating the axle, the engineering problem left the controlled environment of the workshop. The rear wheels now had to climb real grades, the front wheels had to follow imperfect roads, and the operator had to control a heavy-powered vehicle among people and horses who had never been asked to share the street with anything quite like it. The early trials appear to have shown both how much the Johnson brothers had accomplished and how far the machine remained from practical road transport. According to the later 19th century engineering account, the wagon was tested on neighborhood roads that were not fully paved, conditions severe enough to expose weaknesses that a smooth demonstration surface could have hidden. The engine and boiler were not described as having abundant reserve. Instead, the tests revealed a lack of power in both, yet the wagon could still continue running for extended periods and overcome notable rises in the road. The combination is important because it prevents two opposite distortions. The machine was neither a useless contraption barely capable of crawling, nor a triumphant vehicle ready to replace horses. It was a functioning experimental road engine whose limitations became apparent precisely because it was being asked to perform real work. A grade placed additional demand on the driving axle. Rough ground increased rolling resistance and shock. Uneven surfaces interfered with steering. The wagon had to negotiate those conditions, while its single-cylinder engine delivered uneven rotational force, and the boiler worked to maintain an adequate steam supply. Each difficulty interacted with the others. A rise in the road could reduce speed, causing momentum in the mechanism to fall. Lower momentum made the irregular delivery of torque more noticeable. Greater engine demand consumed steam more rapidly. Meanwhile, the operator still had to keep the vehicle pointed in the intended direction. The street trials therefore turned the Johnson wagon into an integrated test rather than a collection of separate mechanical demonstrations. Steering emerged as one of the most serious practical problems. The great rear wheels supplied movement, but they did not decide where the vehicle went. That responsibility fell to the smaller front wheels and whatever steering mechanism connected them to the operator. On a straight road with room to correct gradually, this might be manageable. In a confined urban environment, delayed response or misjudged momentum could become destructive. Joseph Harrison Jr., writing in 1872, preserved a particularly vivid account of one such trial. His description drew on information from a man who had witnessed the wagon being built and tested, giving the story more weight than an anonymous legend, while still leaving it separated from the event by several decades. According to that account, the machine crossed High Bridge and proceeded up Brown Street. When a change in direction became necessary, the wagon did not turn quickly enough. It mounted the curb and struck roadside structures, damaging awning posts and a window near the corner of Brown and Oak Streets. The value of this incident lies not in treating it as comic disaster. It reveals a fundamental mismatch between mechanical propulsion and the control environment in which the wagon was operating. The engine had done its job. The axle was turning. The machine had enough momentum to continue moving. The failure came from placing that momentum precisely where the operator needed it to go. Propulsion had advanced beyond steering. That imbalance is one of the recurring problems in the history of experimental transportation. Solving motion exposes the need to solve control with equal seriousness. Horses had offered a form of distributed intelligence that early machines lacked. They could respond to reins, but they also perceived obstacles, adjusted their footing, and moderated their movement in ways that were difficult to reproduce mechanically. A steam wagon transferred those responsibilities to human judgment and mechanical linkages. If the vehicle was heavy and slow to respond, the operator needed more distance and better anticipation. An urban street offered neither reliably. Later descriptions also mention the effect of the steam wagon on nearby horses. Such reports should not be inflated into scenes of universal panic, but the underlying conflict is easy to understand. Steam exhaust, mechanical noise, and an unfamiliar moving structure could disturb animals accustomed to conventional traffic. Even when the Johnson machine functioned correctly, another road user could react unpredictably to its presence. This meant adoption required more than mechanical reliability. The new technology had to coexist with the old system during a transitional period in which both shared the same space. Road quality remained another source of difficulty, but its importance was physical rather than merely inconvenient. A rut could push a steering wheel away from the desired line. A hard impact could transmit force into the frame and machinery. Loose or soft ground increased the effort needed to keep the vehicle moving. Descents created another problem because the mass that made climbing difficult became momentum that had to be controlled on the way down. The surviving evidence does not provide a sufficiently complete description of the Johnson wagon's braking system to reconstruct exactly how every stop was managed, and inventing one would create false precision. What can be stated safely is that reducing steam supply did not instantly eliminate the kinetic energy of a moving vehicle. Once the great wheels and the structure around them were in motion, that energy had to be managed. The Brown Street incident demonstrates the practical consequence more effectively than speculation about specific controls ever could. Repeated trials also brought durability into the equation. A road engine had to endure heating and cooling cycles, vibration, joint movement, axle loading, wheel impacts, and continual mechanical adjustment. A prototype might survive a demonstration while proving burdensome to maintain over regular service. Here, the historical record becomes thinner. It does not give reliable maintenance intervals, operating costs, fuel consumption, or a long service history from which modern estimates can be calculated. Rather than fill those gaps, the surviving narrative itself provides the important clue. After the incident described by Harrison, the steam wagon apparently ceased appearing on the streets, and its later fate is uncertain. That disappearance should not be dramatized, as though one collision destroyed a coming transportation revolution. There is no evidence for such a story. The trials had already revealed limited power, difficult control, road resistance, and the challenge of integrating a large steam machine into ordinary traffic. A single mishap may have ended the visible testing, but the broader obstacles existed before it occurred. The real turning point had been reached earlier, when the Johnson brothers proved that the wagon could propel itself. Once movement was possible, the criteria for success became much harsher. The machine now had to be judged by control, durability, repeatability, operating demands, and economic usefulness. These were problems that could not be solved inside the cylinder. They belonged to the relationship between the vehicle and the world through which it traveled. Philadelphia's streets had shown that self-propulsion was only the beginning. For steam road transport to become ordinary, the environment around the machine would have to change as much as the machine itself. That surrounding environment strongly favored established forms of transportation. The Johnson brothers were working from a small engineering establishment, not from an industry equipped to manufacture, distribute, maintain, and operate powered road vehicles at scale. A steam wagon required specialized knowledge that ordinary carriage ownership did not. Boilers had to be inspected and maintained. Engine components required adjustment and lubrication. Fuel and water had to be available. Operators had to understand the machinery while also controlling the vehicle. Repairs could demand skills and components outside the routine experience of coach builders or stable workers. Horse transport had its own substantial costs and limitations, but it existed within a mature network. Stables, feed suppliers, blacksmiths, harness makers, carriage builders, drivers, inns, and watering arrangements were already part of daily transportation. A new mechanical system had to compete against that entire structure rather than against the horse in isolation. This helps explain why a steam wagon capable of moving under its own power did not automatically offer an economic advantage. The relevant question for a potential customer was not whether the machine was impressive. It was whether it could perform useful work often enough, reliably enough, and cheaply enough to justify replacing a system people already understood. The surviving record does not contain the figures necessary to calculate that comparison for the Johnson wagon. There is no responsible basis for inventing its construction cost, fuel bill, repair frequency, or carrying economy. The absence of an enduring production enterprise nevertheless suggests that the conditions necessary for commercialization did not emerge. Road quality made the challenge still harder. Uneven surfaces increased wear and uncertainty, but the economic consequence mattered as much as the mechanical one. Greater stress meant more inspection and repair. Slower travel reduced productivity. Difficult steering increased risk. A route that could be negotiated in favorable conditions might become much less attractive after weather or heavy traffic altered the surface. Strengthening the machine could improve durability, but additional material added mass and increased the demand on a power plant already described as limited. Engineers were trapped in a familiar compromise. Solving one weakness could intensify another. The wider development of steam power during the same period shows that the technology itself was not the problem. Steam engines were succeeding in environments better suited to their characteristics. On water, vessels could carry substantial machinery, fuel, and passengers without confronting potholes, curbs, or street traffic. Industrial installations could place the engine near maintenance and supplies. On land, another infrastructure was beginning to offer a different solution. railways reduced the need for a powered vehicle to steer freely across an unpredictable surface. The route was fixed. Wheels followed rails designed to guide them. Rolling resistance could be more consistent, and the transport system could be organized around known locations for fuel, water, loading, repair, and operation. Railways introduced their own serious engineering problems, including track strength, gradients, adhesion, locomotive reliability, and enormous capital costs. Their advantage was not simplicity, it was compatibility. The machine and the infrastructure could increasingly be designed for one another. A road steam wagon had to fit into streets serving almost every other form of movement. A locomotive operated on a specialized path. That distinction helped give heavy steam machinery a clearer route toward commercial success on rails than on ordinary urban roads. The Johnson wagon should not be inserted artificially into the history of American railways, as though it caused that transition. No evidence shows later locomotive designers treating Nicholas and James Johnson's machine as a foundational prototype. Its relationship to railway development is contextual rather than genealogical. The experiment belonged to a larger period in which engineers were testing how far steam power could travel beyond fixed industrial installations. Oliver Evans had explored one direction earlier. Thomas Blanchard was associated with another early road steam effort. Railway engineers pursued locomotives on controlled tracks. Different experiments exposed different limitations, and the environments that best supported steam ultimately determined where the technology became commercially important. The Johnson machine happened to confront one of the least forgiving combinations: a large steam power plant placed on a freely steered wagon and sent through streets dominated by horses. Its failure to create an industry is therefore less mysterious than it first appears. The experiment had to overcome mechanical, infrastructural, economic, and operational barriers simultaneously. Later road vehicles would benefit from changes that altered that entire balance. Power plants became lighter relative to output. Control systems improved. Manufacturing became more specialized. Roads changed. Repair and fuel networks developed around motor vehicles. Internal combustion engines eventually offered a radically different relationship between weight, range, starting, and operation. None of that means the Johnson steam wagon was simply a bad automobile built too early. It was not trying to satisfy the mature expectations that later defined an automobile. It represented one possible answer to a problem whose final form had not yet been established. Its mixture of carriage steering, huge rear wheels, steam machinery, and direct axle drive shows engineers working within the technological vocabulary available to them. The disappearance of the machine and the limited survival of records surrounding its builders also reveal something about how technological history is preserved. Successful industries generate documentation. Companies produce advertisements, catalogs, manuals, patents, financial records, service networks, photographs, and surviving machines. Isolated experiments can leave little more than a few later descriptions. Nicholas and James Johnson fall into that second category. Their names survive, as does an outline of the wagon and several accounts of its trials, but not enough evidence to reconstruct their personal story safely. There is no reason to imagine bitterness, forgotten patents, secret investors, or a deliberate suppression of their invention. The historical silence is more ordinary and more revealing. The experiment did not create the institutions that would have preserved it in greater detail. By the time motorized road transportation became commercially important, engineers would solve the problem using configurations very different from the Johnson wagon. That does not make the 1828 machine irrelevant. It makes the proper historical question more precise. Instead of asking why Nicholas and James Johnson failed to invent the future, it is more useful to ask what their machine demonstrated about the difficulty of leaving the horse behind. The answer lies not in one component, but in the gap between a functioning prototype and a workable transportation system. That gap is the most defensible legacy of the Johnson experiment. It is tempting to end an early transportation story by declaring that one obscure machine was the first automobile, the forgotten beginning of modern motoring, or a revolution that arrived before its time. The surviving evidence does not require any of those claims. Earlier American experiments involving Oliver Evans and Thomas Blanchard make absolute priority difficult to establish, and the Johnson wagon did not produce a known line of vehicles that evolved directly into the gasoline automobile. Its importance is more modest and, for that reason, more instructive. Nicholas and James Johnson apparently built a road-going steam wagon capable of operating under its own power on Philadelphia streets. They arranged a boiler, cylinder, connecting mechanism, crank, axle, steering system, and wheels so that mechanical force generated on the vehicle could propel the vehicle itself. The trials then exposed what that achievement did not solve. The engine could create movement without making the machine easy to guide. Large driving wheels could carry the wagon across rough ground without eliminating road resistance. Enough steam could be produced for continued operation without giving the system abundant reserve. A vehicle could climb grades and still remain awkward in confined streets. Technical success at one level revealed deficiencies at another. This pattern is more historically valuable than the image of a lone invention suddenly changing everything. The Johnson wagon shows that transportation technology develops as a system. Propulsion must coexist with control. Mechanical strength must coexist with manageable weight. Range depends on supplies. Reliability depends on maintenance. Commercial usefulness depends on infrastructure and demand. In 1828, those relationships had not yet been reorganized around powered road travel. The existing environment worked tolerably well for horses because generations of economic and physical infrastructure had adapted to them. Steam road vehicles entered as outsiders, requiring accommodation before they could provide enough advantage to justify that accommodation. Railway locomotion followed a different path because the infrastructure could be specialized around mechanical traction. The track guided the vehicle. Support facilities could be concentrated along fixed routes. Heavy machinery could be accepted because the entire transport system was built around moving large loads efficiently. Road vehicles required far greater flexibility, and large steam machinery carried penalties that later power technologies would reduce. The Johnson brothers could not know the final form that solution would take, and the historical record gives no reliable reason to pretend they predicted it. Their work belongs instead to a period of uncertainty when engineers were testing many possible relationships between steam power and mobility. Some machines reached commercial maturity, others remained experiments. Those experiments still mattered because they converted abstract mechanical possibilities into observable problems. The Johnson wagon provided evidence that a self-propelled road machine could operate, and the trials made visible the difficulties that followed once it did. The Brown Street incident is revealing for exactly that reason. The failure there was not that the engine refused to move. The opposite problem had emerged. The machine possessed movement that could not be redirected quickly enough. A new form of power had created a new demand for control. The reported shortage of boiler and cylinder capacity offers another example. The vehicle functioned well enough for the limitations of its power plant to become measurable in practice. Engineers could now ask not merely whether steam propulsion worked, but how much capacity was required for the road, load, gradient, and mass of the complete vehicle. Even the eventual disappearance of the wagon has meaning when viewed at the proper scale. It suggests that a working prototype alone could not create the commercial and institutional structure required for technological continuity. The machine left no known manufacturing dynasty, standardized design, or direct lineage of road vehicles. Yet it preserved a moment when traditional carriage engineering and mechanical propulsion were forced into the same frame. The smaller steering wheels at the front belonged to an old transportation language. The immense powered wheels at the rear pointed toward a different one. Between them sat the unresolved problems of 1828. That image is enough for the conclusion. There is no need to turn Nicholas and James Johnson into forgotten heroes, or to claim their wagon secretly contained the modern automobile. Their achievement becomes clearer when the myth is removed. They built a machine that apparently moved through Philadelphia without animal traction, carried its own steam plant, and converted pressure into useful motion at the driving axle. The road then revealed everything else that practical transportation demanded. In that sense, the Johnson wagon did not fail because self-propulsion was impossible. It failed to become ordinary transportation because self-propulsion was only one part of the problem. Nearly 2 centuries later, that distinction is what makes the experiment worth remembering.